an example. Example number 4. Your friend is creating an abstract sculpture that consists of 3 small heavy spheres attached by very lightweight 10 centimeter long rods. We are given the masses of the spheres, m1, m2, m3. What's the object's moment of inertia if it is rotated about axis A? So axis A is shown right here, and so that means that the object is rotating about this axis, so it could be rotating this way or this way. It doesn't matter, but that's what you want to visualize. So if it were rotating this way, that means this whole thing is coming out of the paper to the left and then into the paper that way. So it says that the rods are lightweight, so that means we can ignore the mass of the rods, and we only care about the 3 individual masses, which we can consider particles. We don't care about their size or shape. So we can use the definition of the moment of inertia, which said the moment of inertia is the sum of the mr squared. So what this means is you sum up the masses times their distance squared from the axis. So we can rewrite this as m1 r1 squared plus m2 r2 squared plus m3 r3 squared. So the masses have been labeled on the picture m1, m2, m3, and they are given to us. So what we need is the distances, and these have already been given to us as well. m1 is on the axis of rotation, so it doesn't have any distance from the axis. So r1 is 0. So we can cross out the whole term. And then r2 is a distance from the axis right here to this mass. It's 10 centimeters because that's the length of the rod. So r2 is 0.1 meters. So I'll go ahead and just plug in the numbers. m2 is 1.5 kilograms times 0.1 squared. And then m3, we also want the distance from the axis. Now the axis is this long, right? So you can see that r3 is that distance. Whenever you're finding the distance from one point to another, you're looking at that shortest distance between the two things. So that distance is also 0.1. The mass was 1 kilogram, so we have 1 times 0.1 squared. We plug all of that in, and I got 0.025, and the unit for the moment of inertia was kilogram times meters squared. I forgot to mention it in the previous slide right here. It comes from the definition of a mass times a distance squared. So that was part A of this problem. And remember, the moment of inertia gives you an indication of how hard it is to rotate the object. So the bigger this number, the harder it is to rotate the object. Let's do part B, where the only thing we have done is we have changed the axis of rotation. So instead of being right here, a vertical line, the axis B is at the location of that first mass, but it's coming out of the paper. So imagine a stick coming out of the paper toward you. And so that means that now the object can either be rotating this way or this way, clockwise or counterclockwise. So you can see that's a very different motion than into or out of the paper like in the previous parts. So we're going to do this one the same way. I equals m1 r1 squared plus m2 r2 squared plus m3 r3 squared. And then plug in the numbers. Now this problem has already done some of the math for us. For r3 here, we'll get to it in just a second. So r1 is still 0 because mass 1 is still at the location of that axis of rotation. So that does not contribute to the moment of inertia. So it doesn't, what we're saying is that mass 1 does not affect how easy or how hard it is to rotate this object. So let's look at mass number 2 here. The distance is still 10 centimeters from the axis to that mass. So 0.1 meters. the mass is 1.5 times 0.1 squared. Now mass 3, which was over here, is further away now from the axis. It used to be the axis was right here and the distance was horizontal, but now that the axis is coming out of the paper, the distance is shown on this picture with R3. And we're given the value 14.1, but in general, you'd have to calculate this value because you know that both sides of this triangle are 10 centimeters, so you would have to use the Pythagorean theorem to calculate the 14.1 centimeters. But since we're given it in the picture, we're going to go ahead and plug it in. So that's going to be 0.141 squared times the mass of 1. We add all of this together, and I got 0.035 kilograms times meter squared. So what this means is that when you rotate this object about this axis versus axis A, it's going to be harder to rotate in this case because the moment of inertia is bigger. And that's because mass 3 is further away from the axis than it was in the first part. So I'd like to finish up this video with this last slide here. And what this one is saying is that if you cannot treat your objects as particles, if you actually care about the size and the shape of the objects, then you cannot use mr squared to find a moment of inertia. It turns out that you need calculus to find the moment of inertia of these extended shapes. So we don't use calculus in this class, so we're just going to accept all of these expressions for the moments of inertia of different shapes. You don't have to memorize these. They're given to you on the equation sheet, these first four. So I still give you the rods here because sometimes you might see it on a homework problem, but I tend to leave the test problems to one of these four cases. So even though we don't have to memorize these formulas here, what I want to do is just look at this rod here that is being rotated about two different axes. So hide these expressions, don't look at them, just look at the pictures and think about which one has the greater moment of inertia. The one that has the mass distributed the further away from the axis overall. So in the first case here, you've got some mass that is at the most this far away, while in the second case, when the rod is rotated about the endpoints, you've got some mass that is further away. It turns out that the second case is going to have the higher moment of inertia. So now we can look at the expressions that we are given. 1/12 ml squared for the first case and 1/3 ml squared for the second case. So indeed, this moment of inertia is bigger than that one. So conceptually, I want you to be able to tell me, if you are given several shapes, which one has the higher moment of inertia. We can do the same thing here by looking at the sphere versus a spherical shell. Assuming they have the same masses, which one has mass distributed further away? Well, this is solid, it has mass close and far, but in the shell, all of the mass is far away. So that means that the spherical shell has the greater moment of inertia. And indeed, if you look at the two expressions, 2/5 mr squared for the solid sphere, 2/3 mr squared for the spherical shell, the moment of inertia is greater for the shell, which means that it's harder to rotate. So just to recap moment of inertia, what you're going to be doing is looking at how the mass is distributed about the axis of rotation. The further away that it is, the bigger the moment of inertia, and the harder it is to rotate that object.